So you may wonder how this texture filtering relates to something that you've probably heard of called anti-aliasing. So we're going to talk about anti-aliasing now. So what is aliasing? Aliasing, this is an example of aliasing. There's lots of examples of aliasing. It has a precise definition related to signal processing. And if we have time this quarter, we'll have a lecture on signal processing. But you can think of aliasing as these jaggies and this crazy stuff in the back for the moment. So anti-aliasing, we'd like to fix those things and all other sources of aliasing that we might have in graphics. So where is this aliasing coming from? So consider just our simple basic triangle. When we draw this triangle, we just turn on individual pixels and we get these jaggies along the edge because it's not an exact match. Okay, this is an example of aliasing. Here it is drawn in another way, right? So we have this pointy sets of things and we have all of these jaggies. It's just showing the same thing. Is that really the best we can do? No, we can do better. So this is one sample in the middle of the pixel. And somehow what we really wish we knew was how much of this pixel is covered by this triangle. And we could put some value that was related to that. So rather than just using the one sample and saying it's all on or all off, we can do better. So what if inside each pixel, we haven't changed our screen resolution, but what if we just decide to pretend there's a 2x2 grid of subpixels in here? So this is sometimes called subpixels. This is sometimes called supersampling. These subparts, by the way, are called fragments. That's why we have fragment shaders, right? So instead of having a pixel shader, we might actually do our calculations on these sub things. So we're having a fragment shader, which is later going to be combined into a single pixel. So now we can answer questions that say, oh, look, this pixel hit the triangle 3/4 of the time and didn't hit it here. And this triangle, oh, it hit it half of the time, but it didn't hit it on these others. And then we can go to each pixel, average together the fragments, and get an average value. Right? So by the time we get to this pixel, we don't get full red, we get this 75%. We keep going, each pixel now has some partial coverage value that is going to apply here. So by having more samples inside of a pixel, we can calculate these anti-alias values through supersampling. So we end up with something which is percentages. And we could do this in the color, or we could use our alpha channel to try to control this. There's a couple of different ways we could try to turn this on. So here's our point sampling example again with the jaggies. And here's what it looks with 4x4 samples per pixel. So the picture that I drew was 2x2 samples, but we could do more subsamples. Here's 4x4, and we could get something that looks like this. You might wonder, do we have to do it this way? Could we just generate this jaggy stuff and then just blur this? And then maybe that'll smooth this out. Turns out that doesn't work. There's some math which shows exactly why this is true, but we're not ready for that yet. Maybe if we get to the signal processing lecture. But let me just say that once you've put the aliasing in, you can't get it back out. You have to take some actions before the aliasing actually occurs. And putting multiple samples in a pixel is an example of doing pre-filtering rather than post-filtering. This is post-filtering. And that's sufficient to clean up the boundaries. So you can't just deal with it in post. You have to go and pretend there's extra pixels and sample higher. Min-mapping is also an example of doing this pre-filtering. So we drew this picture with 2x2 samples per pixel, but of course you can put whichever samples. So some graphics companies have started to get fancier and allow programmability of this, where you can say, I want my samples here and here, or I want my 4 samples to be in these positions, or I want my 6 samples to be in these positions, rather than on a regular grid. It turns out if they're kind of randomly placed, it's better. And in addition, I could take different samples on frame 1 and frame 2, so that the total effect that we see, if the frames are going by fast enough and our eye is not really catching it, is more like we have more effective samples. So the sampling patterns can get quite complicated in order to do this super sampling maneuver, but this is a detail. The general idea is we want to get more samples and average together to get something, and this is how anti-aliasing works. So here's some more examples. Here's no anti-aliasing with our jaggies. Here's 4 samples per pixel. Here's 16 samples per pixel. Most of the effect comes from doing it at all, but it does get smoother. This bottom example is from ray tracing or radiosity or something. It's not from OpenGL style. But again, this same thing. This is 1 samples per pixel, 16 samples per pixel, on up to 256 samples per pixel. You can see that things get smoother. Instead of jaggies, this was noise that we were trying to get rid of. But this idea of having super sampling still applies. Here's an example GIF just to show why we might care about this. So I've been showing static pictures, but in animations, it's even stronger, as we saw before in the bunny cubes example. So here's just a line, and you see the jaggies are really bad. And if we at least do, this is post anti-aliasing, and they've actually cleaned up this line fairly well somehow. But you can see I've still got flashing as my line moves upwards in this bottom example. And if we do, this is 8 times super sampling using this particular pattern, you can see this line appears to move much more smoothly, right? So we can get our animated objects to look more smooth.